Hi, my name is Krishna Maran, and this is Physics 2212 Lab 5. So the purpose of this lab was to collect observational data of a magnet falling through a conductive tube of aluminum foil and to model that interaction through a coding closed script. And then you also had to compare the computational predictions with the data that we observed. So the main two physics principles we will be using are Faraday's law, which is that a non-constant magnetic field induces a current and an EMF induced in a surrounding coil, and the Biot-Savart law, which is where that currents are produced in a magnetic field vertically and put the magnet above the top opening, and then we recorded it with the smartphone with the magnetometer app, and then we measured how long it took to fall through the tube, and it was a lot different than free fall because it went a lot slower. So the data we received after doing 5 separate trials were that the average time it took for the magnet to fall was 1.18 seconds, and the length of the aluminum foil tube was 0.3048 meters, and the width of it was 0.005, and the inner radius was 0.02 meters, making the outer radius 0.025 meters, and then mu of the magnet from the previous lab 3, was 3.11 am squared, and then the mass of the magnet was 0.0241 kilograms. Now for the computational model of the lab. First, we had to define the properties of the magnet with dipole points. So as you can see, mu of the magnet and the mass is also there. And we also had the calculation from the previous lab to find mu of the bar and mu hat. And then we also had to define how to find the magnitude of a magnetic field if there is a dipole, and that would be mu over 4 pi times 1 over the magnitude of r cubed times 3 times mu times r hat subtracted by mu, and that would be the magnetic field. And then we also needed to define the formula to find the flux dt, and the way that you would do this is for the numerator, it would be 3 over 2 times 4 pi times mu over 4 pi times the mu constant times the distance times the speed times the radius of the ring squared, all over the square root of the radius of the ring squared plus the distance squared. And then that would get you d flux dt of the magnet inside. Now for the simulation loop of the code that actually creates the graph. So as you can see, the graph on the left shows that the time that the magnet fell according to the computational model was 0.988 seconds. So from the code, how they determined this was that we calculated the gravitational force on the magnet first, which is gravity times the mass, obviously times a -1. And then for the ring in the tube, we computed dt for the ring due to the falling magnet. And then we colored each ring according to the current, and then afterwards you have to assume that the magnetic field is assumed to be asymmetric, and that is how you find the magnetic field on the ring and on the magnet by using the formulas earlier from the initial conditions. And then you use that to find the magnetic force on the magnet, and then F net would be the magnetic force plus the gravitational force, and then you would find the bar's velocity and position by doing the velocity update and position update formula, and then you would graph that in a velocity versus time graph to find that it is 0.988 seconds. So now to conclude, we have the two discussion questions. So the first one, what if the resistivity of the conductor was reduced as close as possible to 0, and how would the dynamics of the falling magnet change due to this? So this would mean that the current would increase and the magnet would fall more slowly, and since the current increases, the magnetic force would also increase. Next, what if the holes or slots were cut into the tube, and how would this affect the ring currents in your model? This would mean that the magnet would fall faster, and then the magnetic force along with the current would decrease. Thank you for your time.